Right now, the air in a typical office is full of invisible, high-speed data. Every laptop, tablet, and phone shares a single localized superhighway to communicate. But sharing space creates a physical problem. If multiple devices attempt to send data at the exact same fraction of a second, the signals collide. When radio waves or electrical pulses meet on a shared medium, they don't politely slide past each other. They physically corrupt one another. The result is pure noise, destroying the information and forcing devices to try again from scratch. To prevent a shared connection from collapsing into constant interference, network systems use a Medium Access Control, or MAC, protocol. It acts as an invisible traffic controller, setting rules for who gets to speak and when. The simplest government strategy is known as random access. Under these rules, devices don't ask for permission. The moment they have a packet of data ready, they transmit it.
This approach began with one of the earliest wireless networks, ALOHA Net, developed in Hawaii. To connect computers across the islands, researchers built a system that simply broadcast data over the radio and waited for an acknowledgement. This animated diagram shows how random access deals with the inevitable collisions. When two packets launch and destroy each other, the sending devices don't retry immediately. Instead, they wait a randomized amount of time. By rolling a digital dice, the protocol ensures the two devices don't retransmit at the exact same moment and collide a second time. Engineers improved this process with slotted ALOHA by introducing a network-wide heartbeat. Devices must now wait for synchronized time slots to sweep past before they launch. Aligning everyone to a grid cuts the window of vulnerability in half. A further evolution, carrier sense, requires devices to actively listen to the channel. A scanning beam checks for existing traffic. If another signal is already moving, the device holds its packet back. Listening helps, but physical constraints still apply. Because signals take a microsecond to travel, two distant devices can both sense a quiet channel, transmit simultaneously, and still collide in the middle. On physical copper wires, devices can monitor electrical levels while transmitting. This allows a technique called collision detection. If a device hears interference mid-transmission, it blasts a sharp jam signal across the wire, ensuring every connected computer knows the data was corrupted. Wireless networks cannot use this method because a device's own broadcasting antenna is too loud to hear incoming interference. Wi-Fi networks instead use collision avoidance, forcing devices to complete mandatory randomized countdowns before they attempt to speak. Random access excels in environments with unpredictable, bursty traffic, like casual web browsing. The downside is scalability. As more devices join the network, the airspace becomes congested, collisions multiply, and overall efficiency drops sharply. To solve the congestion problem, engineers take the opposite approach. Controlled access eliminates collisions entirely by forcing every device to take a highly regimented turn. As we see in this animated diagram, a reservation method requires devices to digitally book an upcoming slot. The board fills up sequentially, guaranteeing a clear path for the data. The trade-off is the delay required to organize the schedule before any real information moves. Another method is polling.
A central master hub systematically cycles through every connected device, asking if it has data to send. A device is only permitted to transmit when spoken to. Polling cycle stops, paralyzing the network. Token passing decentralizes this control. The devices arrange themselves into a logical ring, passing a specific digital token continuously. Permission to speak is granted exclusively to the device currently holding the token. Controlled access delivers guaranteed collision-free delivery. This predictability makes it ideal for critical industrial machinery where timing is absolute. But the constant administrative overhead makes it too rigid and slow for the dynamic demands of the modern internet. A third strategy, channelization, bypasses the turn-taking problem entirely. It alters the physical use of the medium to allow everyone to transmit at the exact same time without interference. This animated diagram illustrates frequency division. The available communication spectrum is split into dedicated, isolated lanes. Because each device broadcasts on its own unique frequency, multiple packets can travel side by side simultaneously. This method formed the backbone of traditional broadcasting and early satellite communication. Large Earth stations relied on precisely separated frequency bands to manage concurrent global transmissions. Here, in this animated diagram, we see time division.
Instead of splitting the frequency, the protocol grants devices the entire bandwidth of the channel, but only for microsecond, rapidly repeating time slots. The most complex approach is code division. All devices transmit across the same frequency at the exact same time. The signals tangle into a chaotic knot of light, but each device applies a unique mathematical code.
A synchronized receiver uses that specific code as a filter to cleanly extract a single solid signal from the overlap. Code division effectively treats competing transmissions as background noise, extracting only the relevant mathematical pattern. This robust ability to handle dense, overlapping signals made it a foundational technology for mobile telecom networks. Channelization achieves massive, simultaneous scale. The cost is the immense engineering difficulty required to divide physical frequencies or process overlapping mathematical codes in real time. Every shared network relies on a specific set of rules. Engineers must choose between the flexible chaos of random access, the strict guarantees of controlled access, or the complex physical slicing of channelization. This coordination is why home Wi-Fi stays functional even when multiple devices stream simultaneously, and why thousands of mobile calls cross the same city block without interfering with one another. Network design is an exercise in compromise. An architecture that handles millions of erratic mobile phones cannot provide the millisecond precision required by a factory robotics line. The accomplishment of a MAC protocol is its silent, automated coordination. It orchestrates millions of competing digital demands across sprawling infrastructures without human intervention. Beneath the surface, these protocols work continuously to manage the traffic of our daily lives, ensuring that shared communication remains functional, even as our digital environment becomes more crowded.